Hi, I'm Kevin, and welcome to my cave. Today I want a source of audio white noise. I want to close my eyes and imagine myself on a tropical beach, listening to the sound of the sea and the gentle sighing of the wind through the fronds of the palm trees. Who am I kidding? It's just white noise. But I need it for another demo, and so I'm kludging together a noise source. I'm impatient, so I want to make it out of parts I have on hand. I'm going to use the fact that the current through a Zener diode varies almost randomly if you derive it at much less than the recommended current. But that works best with diodes with a Zener voltage more than about 5 volts. And I don't have one on hand. The only ones I found in the box were 2.5 and 3.3 volt ones, and those work differently. So I'm going to do something strange. I'm going to apply a reverse voltage to the base emitter junction of a transistor. According to the datasheet, this is a no-no. And in fact, it will destroy the transistor for other purposes. After I abuse it in this way, the current gain of the transistor will likely be a fraction of what it once was. So I'll clip off the collector lead even before I start, so that the transistor won't go back into stock. What happens when you exceed the breakdown voltage at the base emitter junction is that the junction starts to behave like a very noisy Zener diode. For typical general-purpose transistors, the Zener voltage will be about 7 volts. While the average voltage is more or less constant, the current through the junction flows in discrete tiny pulses at random intervals. The current has to be held to a tiny value, or else the transistor will destroy itself entirely. So the voltage changes corresponding to the little current pulses will also be tiny. The voltage will have to be buffered and amplified. So let's build up a circuit. The one I'm going to use is a classic shown on the schematic here. I'm using two N4401 transistors because I had some handy, but any general-purpose NPN should work. What will also work, if you like, is any Zener diode of about the right voltage, such as the 1N5635 or the BZX79CV8. Wow, that last one is a mouthful to say. Because the bias network is a little unusual, let's look at it in detail and work out the DC biasing. Q2 is a straightforward common emitter amplifier. Looking to its base, we'll see a diode drop combined with the virtual resistance of the emitter resistor value times the transistor's beta. The datasheet just says that the beta is at least 100. The beta of a general-purpose transistor isn't that well controlled, and varies by a factor of about 3. So I'm going to guess 200 for the actual value, and say that the virtual resistance is 200K. That gives us enough information to fill in the voltages A, B, and C. Ohm's and Kirchhoff's laws will give the answers. Recall that Q1 will drop 7 volts, and a diode will drop 0.6 of a volt more or less. 1 volt across the emitter resistor will draw a milliamp, which will drop 4.7 volts across the collector resistor. The circuit's gain at DC is 4.7, the ratio of the collector resistor to the emitter resistor. At AC, it's boosted substantially by the fact that most of the emitter resistance will be bypassed by capacitor C2. I copied the values from other designs that were floating around on the internet, but my back-of-the-envelope suggests the gain will max out somewhere around 180, will be 3 decibels down or about 130 at 640 Hz, and will fall off 6 decibels per octave at lower frequencies. This filter is to compensate for the fact that the noise from the transistor is heavily biased toward the low frequencies. The output RC network is just to block DC. Its RC time constant puts it far below the audio frequency range. That's about as far as we can get by analyzing this thing on paper. Let's go down to the cave and build it. Here's the circuit set up on the breadboard. Q1 is this transistor on the left, and Q2 is this one on the right. Let me see how I made out with the DC biasing. Q1's emitter is at 9.2 volts. Dividing by the 680K pull-up, the base circuit is drawing 4.1 microamps. Q1's base, actually it's the base of both transistors, is down to 1.6 volts. That makes the Zener voltage of the junction 7.6 volts. Pretty close to the 7 volts I predicted. Q2's emitter is at just a volt, which is one diode drop below the base. That's saying that its output current is precisely a milliamp since the pull-down is a 1K resistor. Q2's beta looks to be about 240. That's a little higher than what I predicted, and certainly it's higher than the datasheet's guarantee. If the output current is a milliamp, then the 4.7K pull-up resistor should drop 4.7 volts, putting the collector at 7.3 volts. And the meter agrees. Now let's get a scope on the output. So here you can see my scope probe hooked up to the positive end of that capacitor on the output circuit. And on the scope screen, you can see what looks to be broadband noise at a voltage range of about 1.5 volts peak to peak. If on the scope I capture a single trace and zoom in on it, you can see that it's random excursions in the voltage going up to quite a high frequency. Because here on this horizontal scale, I've got just 20 microseconds per division. I want to do some more detailed analysis on this waveform. So let me capture it to a USB drive and take it out of the cave and to my computer. Off camera, I told the scope to take 120,000 samples of the output voltage at 5 microsecond intervals and save them onto a USB stick. I brought the stick back from the cave to analyze the results on the computer. First, looking at the bias points, I found that the Zener voltage of the noise transistor junction was a little higher than what I modeled, 7.6 volts instead of 7. The beta of the buffer transistor was also a little higher than the model, 240 instead of 200. The emitter and collector voltages of the output transistor were exactly as predicted. Good enough to go ahead with. Next, I wanted to see if the noise is actually Gaussian. I histogrammed the voltage of the 120,000 points and got this distribution. There are some strange step irregularities, which I'm pretty sure come from the way that the scope is quantizing and storing the data. The values in its output file come out unequally spaced. If I plot the cumulative probability density, though, and compare it with a Gaussian, the agreement is nearly perfect. I'm prepared to say it's Gaussian. I also wanted to see whether its frequency spectrum is nearly white noise, so I plotted a spectrogram of the sequence of 120,000 values. The results look very promising. The fall-off at the low-frequency end is below the audio range. So I think I have a winner here for a quick and dirty white noise source. Next time I'll most likely use that source for something. Until then, stay safe, stay healthy, and stay curious.